All right. I was asked about vectorization and what this means, and or what I mean when I talk about vectorization here. And to a certain degree, Olaf already gave you a couple of pointers towards vectorization. Let's start with the dot product. The dot product is basically taking two vectors, multiplying the elements and summing them up. Looks about like this. So I have two vectors, arrays, whatever. I multiply each of the elements with each other, and then I sum up the whole thing. Now, yes, this is a dot product, but actually we can also think of this as a map followed by a reduce operation or a reduction operation. But let's first write a simple Python code for this. So I start my sum at 0, and I just loop over the elements of V, hoping that W has at least as many elements as V here, and calculate the sum that way. If I want to express this as a map, actually the preferred way to express maps in Python, actually the map keyword or functionality is supposedly being dropped eventually, is through a list comprehension. So who's not familiar with list comprehensions? Okay. A list comprehension is, actually, I think then I'll go briefly interactive. Scary. All right. If I want to generate a list, I could do it like this. Well, and now I have a list V. Another way of writing this is by turning this around, and this is now called a list comprehension. Rather than generating a list and adding element by element, I write an expression that looks like this. I put the loop at the end, and then whatever basically is the output here gets added to the list. Now, this is about the simplest expression that I could do, but I could easily also take the squares, for example. Now I have the squares here. Yeah. Behind it. With the conditions, I'm never quite sure where to put them. So now I'm only taking the ones that are divisible by 2. you can make these list comprehensions almost incomprehensible. I'll have a nice example of that maybe even this afternoon. But that's the basic idea behind a list comprehension. It's more efficient than writing the loop and doing the append in terms of code. And at least for simple list comprehension, it's also easier to read once you get used to it. All right.
That's why I called it one-line loops.
So here I'm doing the same thing. Here's my for loop. And this is the operation. This will generate the list. And I'm converting it into a NumPy array right away. Now my second step, now I have mapped all the elements to their product, going element by element. So I now actually have a list of elements that is of the same length as v. Now I want to sum them all up. I could still do that in this loop. So this would be still very Pythonic map reduce. With NumPy, I can do this a little more easily. Instead of having to think about this loop and explicitly creating a map, or basically a new array with just the elements being multiplied, in the loop, I can write a NumPy like this. Right? It's much easier to read. I know that in NumPy, this actually means multiply all the elements by v with all the elements of w and generate a vector that is of the same shape again. And then I can use the NumPy sum on this. These are now both vectorized operations. This loop is actually done in C. This is not done in Python explicitly, but in C. It's much faster. And maybe take a time it operation to it when you go through the notebook to actually see that it's faster. And then I do the sum. So here I have the map, and here I have the reduce. Also, the sum can be done in optimized ways. We don't actually know how the sum is done here. Of course, dot product is what the dot function does. So NumPy has this all implemented in one function, and this function is linked to fast math libraries. All right. Okay. By the way, the dot product since Python 3.6 can also be written just as v at w. It's one of the first operations that actually came from the scientific community and made it into the core language. UFuncts, universal functions, are functions that act on an array or several arrays and return a vector of the same shape as the input arrays. If it's returning a different shape, it's actually called a generalized U function. One of the functions that are traditional U functions actually was the multiplication that we just saw. So when I wrote U times V, that's actually a U-func. It acts on all the elements of the array. And the dot function is a generalized U-func because it takes, for example, a vector or two vectors as input, but generates then a scalar as output. So U-funcs are the bread and butter, actually, of NumPy. functions implemented in NumPy that act on whole arrays are fast because they're usually done in machine code. Let's take an operation that is not always implemented, or usually not implemented in NumPy or in a package, and that's a stencil. For a stencil, we usually have values from the neighbors. We apply some operations to the values of the neighbors and write them into the middle of our cell. So, for example, I have this grid here. Each of these colors represents a number. And I want to calculate the value of this cell here, this yellow one, for the next step as the average of the neighbors. That's a typical stencil operation in 2D. Quite a few solvers, some Laplace solvers, are actually implemented through stencils like this. All right, and I can do this explicitly. So here I'm doing the average. I have this two-dimensional array that I'm looping over. Here shape of 0, shape of 1. And I'm calculating my b variable, my next state, my next step, as a quarter, and then just adding the elements. These here are just for the boundary conditions. So I'm basically taking all the neighbors and average them. And this would be like the first, this was our input matrix, and this is what it generates after one step. That's probably how most of you would do it, just by doing these two loops. Unfortunately, this is fairly inefficient in NumPy. These are lots of accesses to individual array, elements of an array, not even necessarily continuous. It's not as bad as it used to be. Actually, accessing a NumPy array element used to be much more expensive than accessing the same thing in a list. This is no longer true. But this is not an optimal way to do it in Python, NumPy. Instead, you can do something like this. What am I actually doing? I have this array. I have this two-dimensional block. And I want to generate a new one by averaging. OK, so I need the neighboring blocks. So I shift them each by one element. And then basically add those shifted elements. So if I were starting like this and I do this, then I can add the two that are now on here. I do the same thing, one up, one down, one to the other side, and then I have these four elements that are actually lying on top of each other. Now I can use NumPy's ufunc plus. In this case, it acts on the whole two-dimensional array to add these elements and do a quarter. Now, this function acts on the whole array at once. In C, maybe even parallelized, rather than doing loop by loop. And here again, same starting, sorry, this is one iteration. No, same starting value, and this is the first iteration. So the results are actually identical. But the second version is much faster. So that's, yeah?
Excuse me, the memory consumption is the same?
I'm sorry?
The memory consumption is the same?
No, memory consumption is larger. Potentially, at least.
Potentially, yes. I'm not sure. Actually.
Yeah, that's true.
Can do that in place.
If roll does in place.
I don't know.
Yeah. Potentially it's larger. That is.
Should we be thinking about that role as allocating a new array, or just returning a different view on the same array?
I think it should return a new view. Therefore, I think
that's why we are wondering.
I was not sure. I think it is much more efficient to just use a new view of that. And in particular, as a role can also be rolling along more than one dimension at once. I'm pretty sure.
It probably does generate a view, in which case it wouldn't take extra memory. Who has heard of the Mandelbrot set before? Ah, good. You'll be implementing it. That's part of the reason Olaf mentioned the complex numbers earlier in the NumPy notebook and the mesh grid function. So what I want you to do, let me briefly explain the Mandelbrot set. The Mandelbrot set is a set in the complex plane, set of points in the complex plane for which this sum or this series does not diverge. And here Z and C are complex numbers. C actually represents the point. And this is the iteration variable. The series diverges if at any time the magnitude of Z of I becomes larger than 2. Now, since it's not really practical to do this to an infinite number of iterations, you usually set some limit, 10, 100, 1,000, and say, well, if it hasn't diverged by then, I'll just call it part of the Mandelbrot set. This code implements the Mandelbrot set. Well, actually, it implements the core algorithm, the escape time algorithm. It takes a point in the complex plane, P, so a complex number, and a maximum number of iterations that I called max time here. It initializes Z to 0 as a complex number. And then at most for max time iterations, it does Z equals Z squared plus P. That really shows you that Python knows about complex numbers, because here I'm not using anything about the conjugate. Complex numbers are an integral Python type, obviously designed by engineers, because no physicist or mathematician would ever write a J there. So if the magnitude of Z ever goes above 2 within this time, we return our iteration number. And if we get through the whole loop without doing this, we return max time. Your job will be to do this in a vectorized version with NumPy arrays, mesh grids, and not do loops over all the elements. So I want you to basically calculate this escape time for all the points in the complex plane at the same time using NumPy. So rather than doing a loop, you think of this as one big chunk, and you're applying operations to this one big chunk. It's not trivial, especially making sure that you don't overwrite escape times that you already set, but it's doable. The notebook here is called Think Vector. So go through the notebook first. There are a couple of more things than I showed, like in most of the notebooks, and then start with the exercise.